and the deployable side. And we've got a great host of experienced gentlemen here, and I'm going to let them introduce themselves. So Steve, over to you.
Yeah, hey everyone. My name's Steve Arnold. I'm a deputy executive at Johns Hopkins Applied Physics Lab, overseeing what we do for space formulation. So this is dealing with dreaming up and coming up with new mission concepts. Where do we as a nation want to go and explore the solar system? How do we do that? What are the technologies that need to go into that? And I think power is fundamental to everything that we do. So happy to be here, Ken. Over to you, Chris.
Chris?
So my name is Chris Coker. I'm Vice President of Civil Space and Civil Space Programs and Robotics at Maxar Space. We build spacecraft for a wide variety of missions for commercial customers as well as civil space and for national defense as well.
Andy Williams, I'm with the Air Force Research Lab. I am the Deputy Technology Executive Officer for Space, integrating and executing the entire space portfolio across all of AFRL, all 10 technical directorates.
All right, and Ron Birk with the Aerospace Corporation. I serve as the Principal Director of the Space Enterprise Evolution Directorate, where we focus on the areas of space that look different in the future than they do in the past. And we are specifically focused on solutions to advance capabilities, have end-to-end integration in order to outpace the threat.
Thank you. With Redwire, we have a ROSA solar array that has been powering the International Space Station for the last couple of years as an auxiliary power to keep that alive. Our ROSAs have flown and redirected an asteroid. They are flying in GEO, they are flying in LEO, and as we're looking at it today, there's an oversubscription of power demand out there between constellations, exploration, and just the demand of this new space era. And we're going to talk about it today, about what has been working, where do we need to go, and what's next. So first question for the group, and we'll just go right down the line, starting with Steve. What have we seen that has worked really well?
So Ken, I'm going to pick up on your rollout solar array that you brought up. So just to kind of foot stomp that a bit, that technology was enabling for the DART mission that the Johns Hopkins APL built for NASA. An incredible achievement in technology. And in fact, some of the technology investments for that go back several years into some of the early investments from NASA. And so we needed that power supply for our DART mission, which is humanity's first attempt to move something in space, and it was fabulously successful. But I think what we're seeing is that as these technologies roll out, you need to not just have a technology looking for a problem, they need to be ready to go as a solution, and we as kind of conceivers of new missions need to integrate that in from the very beginning, like we did with ROSA. So I think that as long as the mission technologists know those burgeoning technologies, I think they're going to get a chance to fly, and that's really what we need to do moving forward.
Yeah, I would say the ROSA has been an enabling technology, not just on civil space missions, but also commercial missions. At Maxar, we have flown the rollout solar array on commercial missions, and the higher the power demand, the more that a mass-efficient solution creates value and is enabling. And we're seeing that also on the Lunar Gateway, NASA's Gateway program, with the power propulsion element, where we are utilizing some of the biggest arrays that I have ever seen.
So the key piece that I want to highlight of what has worked well is the partnership between industry and the government and government labs and government funding to develop these technologies, right? Most all of the solar cell technology that the U.S. uses in its solar arrays has been developed in partnership with the Air Force Research Lab and industry like Spectra Lab, like Solero, before everybody got bought out by somebody else, to really improve that technology from 18% up to 34 or 35% efficiency. And it was really a great partnership between government and industry that really enabled that. And I do have to point out the ROSA piece, that is a great example of that as well, right? That technology originally started as AFRL IP with high strain composites. that we then rolled into a SIBR program, and the SIBR program has been fantastic in transitioning technology, working with deployable space systems before they were bought by Redwire, to the ROSA array. And the one piece that I don't think people really understand or really know about is the story before ROSA. ROSA was hugely successful, but it really goes to the impact and the importance of sustained S&T over time. People may not realize this, but ROSA was the 4th attempt by AFRL to do a technology like that. We actually started in the late 90s with a program called Power Sail, and it was a fantastic failure. But we learned what we shouldn't do. We learned the things that we needed to fix, and we tried again, ultimately getting to the point where we found out that the high-strain composites that were the driver behind ROSA was the technology approach that we needed to do. And I think that long-term investment, that collaboration between government and industry, leveraging things like the SIBR portfolio, have been the fantastic successes of where we are at today.
Thanks.
All right. Well, I'll certainly pick up on the ROSA bandwagon. An absolutely fantastic, right, capability and technology. But in order to not have honorable mention for other power sources, RTGs, right, radioisotope thermal generators, very important for being able to provide power when solar is not in position to do that, and where a relatively modest amount of power is needed over a long term. So those have certainly worked very well. And we are appreciating the progress that's being made for small nuclear reactors as sources of power, Draco program and others, and seeing that continue to mature so that we have the availability of those sources. And just want to pick up on the point of the partnerships between government and the private sector, and the value of the test beds and proving grounds that have been common to both, to help to build that confidence in these innovative capabilities so that they can be accelerated to get into space.
Right. Thanks, everyone. You know, I do want to mention that the ARFARE program was very instrumental in making ROSA capable, and I mean, it took 10 years before we even did a space station experiment, and then it took another 3 or 4 years before we actually got it on a mission. And I want to thank both Steve and Maxar with Chris, who believed in the technology and took it forward. But this is not about ROSA, this is more about power. So appreciate it. But I just wanted to do a shout out to you guys. What are the key innovations we need to address to meet power demand and to address constellation and exploration goals? And I'll stop with you, Ron. You could jump back into what you were just talking about.
Yeah, I appreciate that, Ken. So yeah, we'll pick back up in terms of the availability of small nuclear reactors is a really key innovation that is clearly going to be beneficial to provide a higher level of power for essentially the kinds of infrastructure that is needed, in particular for cislunar and lunar surface applications. There's a need for on the order of tens, right, of kilowatts. So we're going to need, and steady state through the solar, the lunar rather, day and night. So the nuclear power is going to be increasingly important in that regard.
Thanks, Ron.
Yeah, there's kind of 3 areas I think are really key to the innovations of where we need to go. The first is in manufacturing technology. How do we make solar cells, solar arrays more cost efficient? How can we build them at the scale that we really need to for these growing proliferated constellations? That is only going to become more and more challenging as we start to fly not just thousands but tens of thousands of satellites in space. So I think a key piece is the manufacturing piece. The next kind of key innovation is where do we go after 35% solar arrays, right? IMM, triple junction, we could keep going to 4, 5, 6, 7, 8 junction, but that's got diminishing returns based on the amount of funding that goes in there. What's that leap ahead technology that gets us to 45, 50%, closer to what the theoretical limit for a solar cell would be? And then the last piece is, what is life after solar? It's going to end. We can't be on the solar bandwagon forever. So what comes next? Is it nuclear? Is it some other technology approach. Is it a fuel cell? If we have a logistics economy, can we go down that approach? So I think that's the other big question: is what is life after solar?
Thanks, Steve.
I could definitely jump on the bandwagon of what's life after solar, but I won't. One thing I will say, it's important to understand that as power demands get higher and as spacecraft get smaller, form factors get smaller, there are other innovations such as thermal management, thermal control that need to be a part of the solution space as well. More power by itself only gets you so far. You have to do something with that power, and specifically the thermal management. And playing off what Ron had talked about with nuclear power, certainly being part of the future ecosystem, you got to start thinking about your power management boxes and things like that being designed to work in a locally higher radiation environment around reactors and things like that. Throwing mass at the problem is always an easy go-to solution. It may not be the right problem at the system level for enabling a mission.
Thanks.
Yeah, and I just wanted to pick up on kind of the lunar example that we're talking about. I think this is a very tangible one in terms of how do we have a sustained presence on the lunar surface. Power is fundamental to that. So I think we really need to be, as a nation, leading in this area, as individuals or technologies, and startups think about what is the power that's actually going to be available from an infrastructure point of view as they make investments to go explore some of these places. I think we really need to innovate in that area, get some clarity there, raise the TRL of some of these concepts if we want to have a vibrant cislunar and lunar economy.
As we talk about nuclear power, are there risks associated with that could be mitigated in a different way, or is there another source that we could consider? I went off script.
Well, no, I think nuclear, with the RTGs, in fact, all right, so if you look a couple booths over there at the APL booth, we have a Dragonfly model, half scale, that is going to go to Titan, which is a moon of Saturn. It's propelled and powered by an RTG. So NASA's really good at that. They've developed that. Several missions, that's kind of a known and reliable technology. But we do need to be starting to think about other types of ones. And for example, Stirling technology comes to mind. There's some early investments in that really need to be matured and paid off. But I think there are some non-nuclear options that we need to be looking at as well here.
Chris, any comment?
Yeah, I would just, the specific nuclear solution may be different depending on mission. Looking at RTG certainly makes sense. That's been established for many years on different types of exploration missions. But when you start talking about a sustainable infrastructure on the moon, when you start talking about getting to Mars as quickly as possible, you start getting into some fission reactor type of solutions.
For me, the biggest risk on the nuclear frontier is not doing the systems engineering analysis that's required to really understand what we need from a mission perspective, and instead doing what we generally like to do and go for a big shiny object to demonstrate a capability that may or may not actually scale to what is needed for the mission, to the point where we have a long history in the US of funding nuclear efforts that get canceled because the cost balloons and the performance tails off, and it just no longer makes sense. I think we really have to focus at how do we make this a sustained, continued investment in the key technologies that are required to make that a realistic capability. And from our perspective, from a DoD perspective, it really means going to significantly higher temperatures than what we currently operate these systems at, because if my radiator is the same size as my solar array, then I might as well just fly more solar array. And until I deal with the thermal problem, then I'm not going to go anywhere. And the only way I solve the thermal problem is by driving the operating temperature higher so that I can take advantage of the T to the fourth from the radiator.
Thank you.
All right, Andy, I'll take that pitch and pick up. Actually, where I was going to go is in deployment, right? Deploying the nuclear systems, particularly in cislunar. It's a very harsh environment. And also transmission, being able to actually configure an ecosystem relationship, system of systems between not only the nuclear power source, but its ability to be able to operate in that environment for long periods of time and be able to transmit the power to other utility, basically serve as a utility to provide that to other applications through efficient and effective transmission lines. Those are still high-risk technical areas to be developed.
All right. Thanks for that input. What potential enabling technologies do you envision that will help meet the power demand that we're facing right now, considering the proliferation of platforms, constellations, and into the next decade? You know, a lot of people are looking at silicon. They're going back in time. And is that a good thought? What are your thoughts on that? I'll just throw that to anybody who wants to jump in there.
So I'm not sure if that's the right approach.
Okay.
I do think it is part of an approach that starts to make sense of how do we diversify the power portfolio for the nation for space. That's really the fundamental question. If we are dependent on triple junction solar arrays, I think there's limits to what we can do there. We can help with the manufacturing technologies, the costs there. Silicon is one approach, nuclear is one approach, but I really think it comes down to how do we diversify the power portfolio that we have and how do we look at it in new ways. It may not be that I need to develop my own power on my own system. I know we've looked historically at the past and there have been ideas about space power beaming. And I don't want to say that I'm a believer of space power beaming of space to ground, because there's a lot of technology hurdles that we need to overcome there. And we're investigating some of those out of AFRL with our Spider program. But there is still a question of what about space to space power beaming? Do we use laser? Do we use RF? Does it make sense from a constellation approach that maybe we have a power subsystem that we can do economically and then do the power beaming from one location to another? It also may address some of the lunar surface power challenges. So there may be different architecture approaches that we need to look at just beyond the question of solar, nuclear, or other potential power generation concepts.
Thank you.
If I may, Ken, so that I'd like to talk about that a little bit more, because we have talked as an industry about fuel tankers in space for many years and refueling. I think that same model can work for power with the power beaming technology and a space-to-space solution. Envision a spacecraft with a big array or nuclear power, whatever, right? Generating power that's supplying multiple satellites, multiple spacecraft, or even on the ground at the moon at the right time when it's in the shadow. Just having something analogous to a tanker in space, but it's generating power and transmitting that power across a constellation of spacecraft or to the surface of the moon, what have you, I think would be very enabling and would open up a lot of different new use cases and a lot of new capabilities.
Thanks,
Yeah.
Chris. Ron?
Yeah, picking up on these points, right? That kind of takes us into the realm of thinking about power grids. And really thinking about power in space from a utility standpoint, which then drives the need for technologies that are associated with power management, and being able to direct power where it's needed, when it's needed, and being able to manage those configurations, and being able to do the switch offs. We're fortunate here on Earth to have multiple sources of power and a relatively easy, sort of rotator switch between them. We're very likely going to need something to that effect in space. Right.
Thanks. Steve, any comment?
Well, as they were talking, I was just thinking that, like as a nation, understanding the availability of the power, and I'll go back to the example for the lunar surface. I think it's important, especially for kind of the commercial and the investment side, because not every company is going to want to invest in certain technologies. They want to make sure that it's there and available. So I think that discussion about how we kind of have standards and availability is very important to the ecosystem as we as a nation start to explore, off planet.
Thank you. So the next question that was up, we've really kind of answered that one. So I'm going to turn it over to you. What question or what keeps you up at night for the next generation of power?
I'm glad you asked that because I was going to ignore the fifth question and answer that question. So I was going to go off script no matter what.
Good. I'm glad we're on the same page.
Yeah, so my biggest worry is that power is not Gucci. It's critical, but it's not a shiny object. It's just one of those fundamental things. And the challenge that we have in the government is we fund shiny objects. We fund the Gucci things. And I don't think as a nation we put enough money into research, development, and new technologies for power generation. And power generation is a game changer throughout history. In all aspects, not just potentially warfare coming from the DoD guy, but all aspects. And so I think one of the risks and one of the concerns is how do we build up enough of a surge that senior leadership will start to understand and potentially either increase funding or protect funding in power technologies so that we really can create that game-changing capability that is going to give us the edge over other nations, over adversaries in conflict. And it's just something that we need to do, we have to do, but we don't always do because it's not the shiny object.
Yeah, I would like to just play off of that. A couple things to keep an eye on. One, NASA's STMD is investing right now in fission surface power, and that would initially be deployed in a lunar environment and eventually to Mars. So I think that is one to keep an eye on to see what is the investment, what are the technologies, how serious are we as a nation at that. I also think of a couple of other technologies out there that the Europeans are pushing forward, including americium as a source. And what does that look like, and how does that factor in? It might not have quite the capability as like an RTG, but it does have a place. And then the other area within NASA to keep an eye on is they do have an office for radioisotope power systems, the RPS program, which can be under severe, budget threats. So I think you're right. As a nation, where are we investing in these things that are kind of seemingly mundane? They're not shiny objects, but they are fundamental to our nation's capability to be leaders in this space.
It's important to grow the number of different technologies for generating power as quickly as possible. Applications in space, they are growing. The demand for space power is growing, and one of the things that keeps me up at night is, will the growth of this industry and the demand for power outweigh the supply base's ability to provide it, and then drive cost up and become a headwind and a hindrance to this industry that we all really want to grow as quickly as possible.
Thanks, Chris.
Yeah, and sort of in a larger sense, right? If we specifically think about the continued growth in space of all kinds of capabilities, they all need power. Hard to do anything without it. Staying with this lunar theme for just a moment, we've been studying that arena. There's over 80 companies that are developing nearly 100 discrete capabilities against 12 layers of infrastructure. And guess what they all need? Power, right? And so one of the things that keeps me and our team up at night is the balance of the availability of power, which is actually needed as a predecessor to many for the deployment of many of the capabilities. As we've seen with CLIPS missions, it would be, there's a real value proposition to having fundamental infrastructure in place so that every mission doesn't have to take everything with them and thereby be constrained in terms of how long they can last. And that is a really key concern, because the more that can be done for longer periods of time opens the door for even more that can be done for longer periods of time.
Thanks, Ron. I'm going to turn it over to the audience. If anybody has any questions for any of the individuals up here that you've been burning to ask, or ideas that you wanted to share, let's just keep it to questions rather than ideas at this point, though. Any volunteers?
Parker Wishick, Aerospace. I work with Ron a lot, and we do stay up all night dreaming and thinking about this in a nightmare scenario. But how do you propose the industry gets a clear understanding of the demand signal and the expected demand quantity or volume to then ensure that supply meets demand? Well, that seems like some forecasting challenge. And Ron, you can't answer yet.
I'll draft in behind.
So I'll take a stab at that. It sounds like what you're really asking is how do you solve the chicken and the egg problem, right? All space missions need power. And I think what is important is continued funding of the technology developments to provide more power. If, to coin a phrase, if you build it, they will come. All space missions need power. So the more power that can be generated in the most efficient way possible, there are going to be applications there for that. So continued funding for technology development is going to be very important.
Yeah, and I think we as a nation need to be looking at a longer arc here. I mean, you look at the CLIPS missions, and there are all these kind of single standalone things that, have some successes and whatnot. But I think we just need to do better across the DoD and the NASA arena and the long arc of these things and kind of figure out, what is the demand signal. I think power is fundamental to everything that we're doing. And realizing that the technologies, we're going to have some winners and losers, and that's part of it as well. But I think this kind of cross-cutting across DoD, industry, NASA, perhaps even internationally, needs to be looked at very carefully.
And part of what's baked into that question isn't necessarily the chicken and the egg. It's really a risk question. What are other ways we can mitigate the risk of technology, of companies investing in technologies that may or may not go anywhere? And I think that's where the continuation of public-private partnerships, of government investments, where we have fundamental technology investments that we can continue in order to help share that risk across the entire nation and not necessarily put that entire burden on industry, but it's really got to be a partnership because the government's not going to produce solar arrays and solar cells, right? AFRL, we developed the technology, but nobody buys solar arrays from AFRL. We have to transition that technology to industry. And I think that's where that continued partnership comes from, continuing to leverage things like small businesses and SBIRs, some of the other technology investments like the DoD, OECIF, where they're trying to do operational energy. There are a lot of opportunities out there, but we need to do it as a more integrated and holistic approach as we move forward and integrate all of these different concepts together so that we can really drive to a comprehensive and cohesive national picture.
Thanks a lot.
All right. Fantastic.
Here's your big softball.
There you go. The sail is up. Let's see if we can get some wind. So appreciating all of these points, right? One of the key things we were talking about, advancing capabilities, end-to-end integration, outpacing the threat, right? Staying ahead on these matters. In an evolving ecosystem, there's an interesting sort of technology set that can help us with the answer that to the question Parker asked, which is how do you get an aggregate view of the set of needs across the industry, across the enterprise? And one answer is to use a sort of a centralized or a common engineering environment to collect that information. And we're starting to see examples of where digital environments, digital twins, and digital twins of an entire environment are being put into place where it's possible to actually individual organizations provide their needs and have that aggregated on a discretely identifying basis so that that kind of information can be taken into account.
All right, thanks a lot. I'm going to open up for one more question from the floor. And if not, I want to thank you all for joining us, and I hope you enjoyed it. Have a great time. Good night.
Thank you.
Thank you. Thanks.